can see that in this cycle here, this deviation from the steady state value is less than 5%. And starting from here, it is actually less than 5%. So basically, this time from t equal to 0 to the time where the deviations are less than 5% is known as settling time. So you now have not only a characteristic underdamped system, but you have these parameters to characterize a typical underdamped system. Okay. Now we talk about the response of a typical.
Sir, I'm sorry. Can you just repeat about the settling time concept, sir? I could not follow it properly.
Yeah. So the response basically increases, right, from 0 finally to reach a steady state value, the input. But in doing so, for an underdamped system, it actually overshoots the steady state value, then oscillates around the steady state value. Now, 1 is the steady state value. If you draw these horizontal lines, which is about plus minus 5% of the steady state value, that means if the steady state value is 1, you say that 1 plus 0.05 and 1 minus 0.05. And this response, when it overshoots and deviates from the steady state value, when it is coming within that 5%, that means within 0.05, that time is known as the settling time. Because after that, never the deviations are going to be more than 0.05 or 5% of the steady state value. Always after that, it is going to be less than 5% of the steady state value. So the first time, the time after which the output never exceeds 5% of the steady state value is known as the settling time. Okay.
Thank you, sir. Thank you so much. Yeah, it's clear now.
Now, we talk about step response of an underdamped system, similar to how we did for a first order system. In a second order system, for an underdamped system, we talk about if the input happens to be a step input, your RS happens to be a step input, how the response is going to look like. So you have a typical transfer function which relates the output with input. And in this particular case, when you talk about a step input and you are talking about a frequency domain, and you know that the input is not in the time domain, it is in the frequency domain. And for for an input of 1 in the time domain, in the frequency domain, the expression becomes 1 over S, right? If you remember when we talked about the Laplace transformation, when we take a Laplace transformation of a unit function, the value is 1, you get in the frequency domain, you get as 1 over S. So basically, and this is the transfer function. So your output for a step input is going to be 1 over S times the transfer function. So this is basically going to be the output for a unit step input. Now this you may not be able to appreciate because you do not have an inverse Laplace transformation of this entire term. So you do some algebraic modification. And this term, you can actually write the difference of two different terms. So you can write as 1 over S minus S plus 2 j omega n divided by S square plus 2 j omega n S plus omega n square. So basically, if you do the math here, you can go back here. But now you have expressed the single term as two different terms. Now you do further modification. You write this as 1 over S minus, this is S plus 2 j omega n. The denominator, now you write S square plus 2 j omega n S. Then you want to do this as like A plus B whole square. So you have A square plus 2 into A into B. So the B is basically like J omega n. So you add J square omega n square and subtract J square omega n square, and this omega n square is simply brought here. Okay, so we basically in the denominator you add J square omega n square and you subtract J square omega n square. Now this can be further written as 1 over S minus S plus 2 J omega n is here. Then this term becomes S plus J omega n whole square. Right? You can see here A square plus B square plus 2AB. Then plus omega n square you take outside of the bracket, and inside the bracket you will have 1 minus J square. Okay. And
Sir, I have a question, sir.
yeah.
The second part of the denominator, it looks a bit like the equations we wrote like to the poles of the response. So, I mean, would it be related to it in some way?
Which one? Sorry, this one?
If we go to the last equation.
Yeah. So you are saying
Yes, sir. That one, the two poles what we were talking about.
Yeah. But it has a square root in it. Okay.
Yeah.
So they're not really identical as such. But why we're doing, we'll come to know in a while, because we want to. So basically, when you write from here to here, you still do not have an inverse Laplace, because you want to go from the frequency domain to time domain, right? So you want to have an inverse Laplace. So this you further simplify algebraically. So this is basically the same thing I have written from here. Now you rewrite this as 1 over S minus S plus 2 J omega n, then S plus J omega n whole square, plus what you are saying that this term, now we are calling it as the damped natural frequency of the system. Okay, so if you remember in the very first slide, when I talked about the second order system, I talked about damped natural frequency of the system. Okay, so this is what you are saying, that you are familiar with this expression. So this is basically omega d square, okay, which is the damped natural frequency. Okay, so once you write this, then we still do not have an inverse Laplace of this function. So you again adjust. So you rewrite as 1 over S minus S plus this 2 J omega n you split. Okay. So you write, so there is a minus sign here. So you have minus S plus J omega n and then minus again J omega n. Right. So this 2 J omega n becomes minus J omega n here and minus J omega n there. And the denominator is basically written in both. We have a Laplace inverse of each one of these terms. Okay. So if I, okay, you need still further adjustment, because here you have J omega n and here you have omega d. So you have to make this omega d. So you do that by again writing 1 over S plus this term, same as this term here. But you do some adjustment to this term. That is, you divide 1 minus I square square root and multiply 1 minus I square square root. Then this term becomes omega d now. Okay, so you have 1 over S minus S plus J omega n divided by S plus J omega n whole square plus omega n square minus J over square root 1 minus I square into omega d divided by S plus J omega n whole square plus omega n square. Now, we have the Laplace inverse of each one of these terms. So if you want to go from the output from frequency domain to time domain, you can write, so Laplace inverse of 1 over S is basically 1. Okay. And Laplace inverse of this term here is similar to what you see here. So this is from the Laplace table I have reproduced here for your convenience. So if you have a function which is like S minus some constant divided by S minus some constant square plus some other constant square. So this is similar to what you see here, just that your there is a minus sign here, and here it is plus of minus j omega n, right? So this is like S minus minus j omega n divided by S minus j omega n whole square plus omega d whole square. So the inverse Laplace of this function is e to the power at into cosine bt. So the inverse Laplace of this function is going to be e to the power, your a is basically minus j omega n, so that is minus j omega n into t. E to the power at is e to the power minus j omega n into t. Then cosine of bt. So b is basically omega d. So cosine of omega d into t, right? So you got Laplace inverse of this term. And if you take Laplace inverse of this term, this is a constant, so it will come out. And Laplace inverse of this term is similar to what you see here. So you have b some constant divided by s minus some constant square plus b square. And the Laplace inverse of this is basically e to the power at sine of bt, which is similar to this term here. So you have b as omega d and a as minus j omega n. So you have omega d s minus n square plus omega square. So basically this j divided by 1 minus j square comes, square root comes here. Then this would be e to the power at. So e to the power minus j omega n t. Then sine of bt, sine of omega dt. Right. So this is the solution of system subjected to a step unity input. That means you have a step a function whose value is 1. And this should be the output, the response of a step input for an underdamped system. Now, you can do further math. It's the same thing that I have written here. Now, e to the power minus j omega n t, you can take common. So, inside the bracket, you will have cos omega d t plus j into square root of 1 minus j square sine omega d t. And for an undamped case, when j equal to 0, if you put j equal to 0, then this term is going to go. So, you will have basically omega n, your omega d in that case, your omega d will be simply omega n, and which is your undamped frequency. Undamped frequency is basically same as the natural frequency of the system. So in that case, your output will just become 1 minus, so this becomes 1, e to the power 0 becomes 1, this term goes to 0, so it will be simply 1 minus cos omega dt. Now omega d is basically omega n, so omega n into t. Now when you have a when j is non-zero but has a value between 0 to 1, let's say you take a j of 0.1 and omega n as 3, and with these inputs, if you plot, x-axis is your time, y-axis is your response, which is c of time, this ct. So initially, when time t equal to 0, this is 0, right? Because time t equal to 0, this will be 1. And so 1 minus this term will go to this term will go to 0. This is 1. So 1 minus 1 becomes 0. So basically you have 0. And then this is how the response of the system is going to oscillate about the unit input. Okay, so it comes like that, overshoots, comes down, then goes smaller and smaller, but keeps on oscillating, and finally it reaches a stable input value. Okay, this is when the damping coefficient is very small. Now, what if you slowly increase the damping? Okay, so when you go to a damping of 0.5, you would see that it will overshoot, but very quickly it is going to reach the steady state input. Okay, that means here the settling time is very, very small, okay, for a damping of 0.5 compared to that when the damping is small, about 0.1. But when you go a higher damping, something like 0.9, you can see that almost it is behaving like a first order system. Okay, so there is no oscillation in the system. Slowly, gradually, the output basically increases and nicely merges with the input without any oscillation. Okay. This is because your J value is very large. So typically, we can generalize this second order response using this curve that you can see here. Here, this is a three-dimensional plot. This axis is the time axis, omega n into t. And this axis is the J axis, the damping factor. And this axis is the output. Okay. So you can see that for various values of damping factor, the response curve nature is very different. When the damping is very small, you can see that when the damping is 0, this output is basically oscillating about 1. It may never reach the stable steady state value. Okay. And as you provide more and more damping, you can see that the peak overshoot is reducing, and slowly the next overshoot is reducing. That means slowly it will settle down and merge with the input. But as you gradually increase the damping factor, you can see that at maybe damping factor above 0.8, you see that there is no oscillation in the system. The input just gradually increases and merges with the output. So this gives you some understanding about how second-order system behave, the output of a second-order system behave with respect to time at various damping in the system. So I'm just going to change slide here. I need to stop share. Give me a moment, please. So now we take an example of a second order system, and I will take one example that is from a heat transfer thermal application. We took this example earlier also when we treated this system as first order system. Now with additional information, the problem becomes more complex where we have to treat the system as a second order system. Okay. So previously what we studied is that we had an electric bulb. Okay. And we said that the bulb is at some temperature TB and ambient is temperature TA. And the bulb is basically at some capacitance CV. And then we treated this as first order system and say that if you switch on the bulb, how quickly it will reach the steady state. Okay. We did not really talk about what happens inside the bulb. So inside the bulb, there is a filament, right? And if you consider the filament, you can bring in the filament, then you will see that this system with the filament, the bulb and ambient is no longer a first order system. You have to treat this as a second order system. So this is the thing that is studied here. So you are talking about the filament temperature at some TF, okay? And the thermal capacitance of the filament is CF, okay? So because there is some thermal energy storage in the filament. And then this filament is encapsulated by this glass bulb. Okay. And the bulb has a temperature of TB and thermal capacitance of CV. And outside, you have the ambient some temperature TA. Okay. So you have basically the heat exchange between the filament and the glass, the bulb surface, then the bulb and the outside world, which is the ambient. Okay, so you basically now 2 stages we are going to analyze this thermal problem. So essentially, you can construct a thermal model of this system. So you have the electrical energy that is coming is being converted to thermal energy in the filament. So you have heat input from the electrical heating coming to the filament surface. And the filament has, as we said, temperature of TF, the thermal capacitance of CF. And the heat now flows from the hot filament to relatively cooler the bulb surface. Okay, that is here. That bulb has a temperature of TB and the thermal capacitance of CV. And the filament and the bulb are separated by a thermal resistance that is indicated as RF, because if in a physical system, between the filament and the bulb, there will be air, right? So the air will impart some thermal resistance, which is represented as RF, the filament to bulb thermal resistance. Then you come to the bulb surface, like in the first order system, we had the bulb and the ambient, and between the bulb and ambient, you have the thermal resistance, okay, RB, okay, which is the film resistance. Now, you have QF coming from the filament to the bulb, and QB coming from the bulb to the ambient. Okay. So we write down the constitutive relations. So for the thermal capacitance, we have the capacitance C times the temperature change, temperature gradient. C into dt over dt would give us the heat flux. Okay, this is the conservation of energy. Rate of change of object times the capacitance will give you the heat released or heat absorbed, right? This is the first law of thermodynamics. Now for thermal resistance, we have this relation coming from the Fourier law of heat conduction. That is, the temperature gradient is the heat flow rate times the resistance. Okay, in equivalent analogy is the voltage, current, and resistance. Similarly, your temperature drop is here like the potential difference. Q is like the heat flux is like the current, and the thermal resistance is like the electrical resistance. So you have this equation. Now we write these equations specifically for the filament as well as the bulb. If we write down this for the filament, it will be CF times dTF over dt will be equal to the net heat flux. What is net heat flux? Here for the filament, Q in is coming because of the electrical heating, and QF is leaving to the bulb surface. So the net is Q in minus QF. That causes the rate of change of temperature of the filament. Similarly, the capacitance of the bulb times the rate of change of temperature of the bulb will give you the net heat flux. That is, QF is coming to the bulb and QB is leaving from the bulb. So the rate of change of temperature of the bulb into thermal capacitance would be the net heat flux. So essentially, here we have two different equations. Okay. And so you can actually write QF from here. For the thermal resistance, QF you can write is a delta T over R. So which is the temperature drop across the filament is TF minus TB, and the resistance is RF. So basically QF from here, Q will be delta T over R. So QF will be delta T, which is TF minus TB divided by R is RF. Similarly, across the bulb, the QB living here is basically TB minus TA, the temperature of the bulb minus the temperature of the ambient divided by RB. So if we combine these two equations here and these two equations here, essentially we substitute for QF from here and QB from here, we substitute there. Then we can write that CF dTF over dt, that is coming from here, CF dTF over dt equal to Q in, that is here, minus QF, and minus QF is here. This minus QF is minus 1 over RF, TF minus TB. Similarly, the second equation, we can write CB dTB over dt, CB dTB over dt is QF minus QB. So QF is 1 over RF into TF minus TB, and QB is 1 over RB into TB minus TF. So basically, now we have two equations, combining those four equations. So we need to now these two equations into a single second order equation, differential equation. And to do that, we need to choose a single variable to represent the system, and then write a second order ordinary differential equation using that variable. Okay. And so that way we will be able to easily solve. Now we have two different variables, so that is difficult. So let us focus on the bulb and envelope temperature, which is TB. So we need to eliminate TF. Okay, so we eliminate TF and substitute here. So we only have one equation, then we have one unknown, that is TB. Okay. So that is the thing that we are going to do. And to do that, it will be helpful to introduce this operator notation. Okay. So the operator D represents differentiation. So this capital D of function ft is basically d of ft over dt, which you can also write it as f dash t. If you differentiate this function again, you get d square ft, which is basically the capital D square ft, which is d square ft over dt. Dt should be dt square. And that is equal to f double dash t. Okay. So here you write that CF dTF over dt from here, CF dT over dt is basically the same thing you write here. Now, your dTF over dt is basically, your d over dt is written as capital D. And you multiply both the sides with RF, this RF. So you have RF into CF into d by dt, which is d, and then you will also have TF here, minus TF on the right hand side. If you take to the left hand side, it will become plus TF. So that means RF CF D plus 1, the whole thing into TF. Okay. So basically this is d by dt of TF. This is only TF when multiplied. So that is equal to TB, because here there is a minus sign. Here there is a minus sign, so it is equal to TB plus you multiplied RF both sides, so RF into QN. So from here you can write that your TF is going to be RF CFD plus 1 to the power minus 1, because this you are taking to this side, into TB plus RF into QN. Okay. So basically you have now found an expression for TF in terms of all other parameters. So if you substitute this TF in this equation here, TF, then you have only one variable TB. Okay, so that is exactly you do. You basically substitute this expression for TF here. So when you do, and then you do some algebra, you just do some multiplication of RB on both sides. So you have RB into CB into dTB over dt. So which is RB into CB into d by dt. Your TB is here. Then you multiplied RB, right? So this will be RB over RF into TF. Okay. Then you have RB over RF minus TB. So that minus RB over RF into TB goes to the other side, becomes plus. So that is here. And this, when you multiply RB, becomes just TB. So this minus 1 goes to the other side, becomes plus 1. And then you have RB over RF into TF. That is plus, so goes to the other side, becomes minus. And TF is basically this from here. TF is basically that. So you write this, and part of this TF, which is this term, comes to the right hand side here. And then you have TA, minus, minus, so you have TA. So all the terms from, just by substituting for TF from here, you got this equation. Then you do some adjustments, okay, which I'm so if you just open the bracket and do the adjustment, you can see that this equation you're going to get. So RB, CB, RF, CFD square plus RF plus RB into CF into D plus RB, CB into T plus 1 into TB is RB QN plus RF CFD plus 1 into TA. So now this D you write as d square by dt square. So you have RB, CB, RF, CF, d square TB over dt square plus RF plus RB into CF plus RB, CB into dTB over dt plus TB is whatever you see on the right side. You have RB into QN plus RF, CF, dTA over dt plus TA. So basically we have to solve for TB. Okay. So if you take that your ambient temperature is not changing with time, that means your ambient temperature dTA over dt is 0. And you define temperature T as TB minus TA. Okay. Then TA is not changing with time. So dt over dt is dTB over dt. D square T over dt square is d square TB over dt square. So Now you can write this as d square dB over dt square. You can just write d square T over dt square. And here your dTB over dt goes to dt over dt. And TB, this TA goes to the other side, minus TA. TB minus TA becomes a T. And here you have RB into Q in, which is here. And your dTA over dt is 0 because ambient temperature is not changing with time. So this term is 0. So you have basically this equation. Now, for a typical 60 watt electric bulb, the resistance RB is typically has been estimated to be 2 Kelvin per watt, and RF is like higher because it is air, so 40 Kelvin per watt. Capacitance of the bulb surface is 65 joule per degree centigrade. Capacitance of the filament is very small, 10 to the minus 3 joule per degree centigrade. These practically measured values, you can see that the resistance of the filament is very high compared to the bulb resistance. That means if you have a term like RF plus RB, you can just approximate this as RF, because RF is very, very high compared to RB. So you do this approximation and you say that since this is a second order system, the solution to that is of the form xt is c e to the power st. So d square x over dt square is basically s square e to the power st. So you get s square here, and you get s in the first order term dt by dt plus 1 equal to 0. So this equation becomes this when you say that your temperature, in this case it is temperature, so T as a function of time is equal to C some constant times e to the power st. So then from this equation you can go to this equation. So now this, you can actually see that this is nothing but you can express this as the multiplication of two terms. So you have RBCVS plus 1 into RFCF plus 1, which is basically this term, is equal to 0. Now, if you look at these practical values, your RB and CB, RF and CF, RBCB is 2 into 65 is 130. RF and CF is basically 40 into 10 to the minus 3, that is 0.04. Remember, R into C is basically like a time constant. Okay, resistance time capacitance gives you a time constant. So RB and CV, let's call it some tau B, and RF CF, let's call it some tau F. So you can see that tau B is about 130 seconds, and tau F is only 0.04 second. So notice the two widely different time constant. Okay. So the time, the long time scale, that is this tau B, 130 second, is associated with the thermal transient on the bulb envelope, the bulb surface. And it takes about 5 times time constant. So 5 times tau B comes out to be 10 minutes. Okay. For the bulb temperature to equilibrate with the ambient temperature. But there is another time scale, which is a short time scale, okay, 0.04 second, that is associated with the thermal transients of the filament. Okay. And this small piece of coiled wire heats up and cools down far more rapidly than the glass bulb envelope. And from here, we can say that it takes of the order of 5 times time constant will be only 0.2 seconds for the filament temperature to equilibrate. Okay. And that is something you actually see in daily life, right? The filament, which is red hot because of its very, very high temperature, almost instantly cools down, right, to a very low temperature because the time constant is so small that instantly cools down, and then you do not see that radiation coming from the bulb after you switch off. So it says that this fits with our experience in watching the filament temperature collapse rapidly when an incandescent bulb is turned off. So as soon as you turn off, the temperature cools down so rapidly that you don't see the glow anymore. But at the same time, if you touch the bulb surface, it remains hot for a long time because the time scale of cooling is very large. It's about 10 minutes or so. This equation is very similar to the second order equation, the generic second order equation that we talked about in the very first class when we talked about second order system, which is 1 over omega n square into s square plus 2j over omega n into s plus 1 is 0. So this is a generic second order equation. And this is similar to what we get from this thermal system. And if you bring similarity between these two, you can see that your omega n will be 1 divided by square root of this term here, which is RB, CB, RF, CF. And 2j over omega n will be RF, CF plus RB, CB. And if you use the numerical values for this example, you have RF, RB, CB, CF. You can show that this omega n is of the order of 0.44 radian per second. And J happens to be about 57. Okay. Now, in this case, if you want to see the poles of the system, so here you have the real axis, here you have the imaginary axis on a S plane, the frequency plane. And you can see that the poles are basically frequencies, and you see that tau b is 130 seconds. So your SB is minus 1 over tau b, which is minus 7.1 into 10 to the minus 3 second. And SF is basically minus 1 over tau f. Tau f is 0.04 second. So SF is about 25 per second, 25 hertz. This is about 7.7 10 to the minus 3 hertz. This is about 25 hertz. And the natural frequency of the system, which is basically the solution to this equation, is, we said, that is e to the power c e to the power st. But here you have two values of s. Okay, one value of s is here, and the value of s is there. So this s is basically minus 1 over tb. This is minus 1 over tau f. So you can write the solution, the simple, the natural response is basically C1 e to the power minus t over tau b plus C2 e to the power minus t over tau f. Okay, so this is how you would analyze a typical second order system, study their response in terms of the frequency and the damping coefficient, if you know the geometrical parameters and the properties of the system. And you can get a solution to the response of the system as well. So I will stop here. If you have any question, we can discuss.
Sir, I understand the concept.
Recording stopped.
Yeah.
I have one question regarding the reference book for this first order and second order system.
Okay.
Main
Yeah. So I think this Dublin that I had suggested would talk about this first order, second order system to a good extent.
okay.
Sir,
Yeah.
speaking of the textbooks, I was just referring the SP Venkatesh book, Athena.
Yeah.
Athena. So for the first few topics which we covered with regards to um, with regards to probability and statistics, they are available in SP Athena, sir, or would there be
Yeah,
any better?
they actually, the Hallman is a better book for the first portion of the course that you were on the statistics
Okay,
analysis. Okay, you please refer to Hallman for that.
okay,
And for whatever we are covering right now, I mean, in fact, with this, we completed our discussion on first or second order system. So this part you would actually find in Dublin. But here on, whatever we are going to cover, the temperature measurement, which we are going to start from the next class, these things will be discussed in great detail in SP Venkatesan book.
okay, okay,
Although
okay.
SP Venkatesan book also will talk about statistics, but I think in Hallman it is actually giving in a much
Yeah,
better.
because I found that in SP Venkatesh, they were directly jumping into a lot of things.
Yeah. I mean, it is actually, talking about many other things that we might not have covered in this course,
Yes,
but you see Hallman.
Hallman.
Okay.
Okay, thank you, sir.
Yeah.
And also I have a question regarding the graphical analysis, sir. So whether we have covered this graphical analysis?
So the graphical analysis we are not doing. I mean, in this course, we have talked about regression. So I expect that, I mean, you all know how to plot in Excel. Okay, so that is something that I do not have to teach you, and that is not the intention of this course. But what we have done is we have gone to the fundamentals of how the Excel works. That means how the regression is done by Excel, right? So in this case, we are able to analytically, by deriving using pen and paper, you will be able to bring out the correlation between X and Y, what this MS Excel is going to give you. Okay. So you can practice problems where you can follow the theory that we have covered in the class to come up with the fitting, curve fitting, let's say linear fit. You can check it quickly. If you have the data set X and Y, you can quickly plot in Excel and you can compare your results with whatever you get. You can also find out the R square value, the index of correlation, theoretically using the formula that we have covered in the class. And you can check the R square value that you are getting from Excel and you can compare. So basically what we have done in the class is what Excel does in the background. Okay. So other than that, I mean, this graphical analysis using Excel is quite trivial. So we are not really covered that.
Sir, with regards to the examples,
Yeah.
would there be any good source where we can find a large number of examples to work on our own?
Yeah, I mean, see, the measurements is such a course that it is very vast. Okay, so
Yes.
there is no single book which will give you like a lot of problems to work on. Okay, so you take Hallman, you will get some example question. There will be some problems in the exercise as well, and there will be this SP Venkatesan book. There may be other books that I have not referred that you are welcome to refer. But as far as I know, there is no single book where a lot of problems will be given for practice.
Okay.
Sir, one last question I want to ask. Can
Yeah.
you go to back? Can you go to the previous slide, sir, if possible,
Yes,
please?
yes.
One more, sir. Probably one more. And sorry, sir, one more probably, yes. Okay. So here the D is basically TF upon DTA upon DT, right? If I'm not wrong.
Yeah. This capital D is basically D by dt.
Derivative of, okay. So if you go to the next slide, sir. Here dTB upon dt.
Yeah. So it's basically D over dt is basically capital D. TB is here.
Okay.
So basically, this operator is here. The variable is sitting outside the bracket.
Got it.
Variable.
So operator can also be
You can, yes.
Sound like algebraic expression.
Yeah. The operator, as long as it is there, it will act upon the variable when it comes.
Thank you, sir. This is a new concept that I have learned today.
I mean, this
Thank you
is
so
a
much.
nice way to.
Yeah.
Sir, I have
you.
one question with respect to the step response.
Yeah.
So maybe can you just go to any one of the diagrams of step response, sir? It doesn't matter.
Okay, let me exit and share that slide.
Like I just need the diagram, I mean the output graph. Sir, I work with PI.
Are you able to see this?
Yes, sir. Yes. Just like a previous slide or the one where we are discussing all the definitions of the response. Yeah, even that is also fine. So basically, sir, I work with PI control every day in and day out, sir. So with a variable input instead of a step response, step input. So because this kind of response is very common to that, we can apply these concepts on the PI control as well, right, sir? I'm sorry if this is a very stupid question.
Yeah, I mean, as long as your the control system is of second order, you should be able to apply these generic definitions to there as well.
I mean, not the definition, sir, because I want to optimize the control, the response of my system based on the varying input that I receive. So I just want to optimize the control. So I was just thinking if I can use any of these concepts to, optimize that.
Yeah, I mean, that would depend on your objective, right? I mean, as we said, if you vary your JI, you can see that how the response is going to be changing, right, in this curve. Okay.
Yes.
So you want to your system to quickly respond to the input, or you want to have a delay, or you never want your system to respond to the input and just keep on oscillating. Depends on your objective, right?
Understood.
Yeah.
Okay.
So I think, some of these theories you have to go through and ponder, and then you have to see how you could apply some of this learning to your practical issues that you are dealing.
Yes, sir. Yes, sir.
Some of them
Thank
may
you, sir.
not be directly applicable, but it could also come bits and pieces that you just have to bring together and apply.
Understood.
Okay, so thank you, and we'll meet again Monday next week. I'll share the slides with you over the weekend.
Thank you, sir.
Okay, sir. Thank you, sir.
Thank you.
Thank you, sir.